All right, so a question like this is basically asking, label each carbon atom with its optimum CCC bond angle. Note, if one or more bond angles are incorrectly placed, a single red X will appear on the top left. So that's just how it's going to grade it in sapling. So the biggest question here, all you need to ask yourself is, how many pi bonds does each carbon have? Right? If it has no pi bonds, what's its hybridization state? sp3. So its bond angle has to be
Should be 109.5.
109.5. And if something's sp hybridized, so sp2 hybridized would mean how many pi bonds?
3.
sp2 would be 1.
One pi bond.
So something like this is a sp2 hybridized.
180.
What's the bond angle for sp2? 120. If you're sp hybridized, how many pi bonds do you have?
That would be
0.
sp hybridized, you have
No, S2.
2.
180.
And what's your bond angle? That'd be something like this, would be 180. For all these, you just need to ask yourself, how many pi bonds are there? How many pi bonds does this carbon have? That's the answer to all this stuff. And then you know the bond angle is based on, because it has those pi bonds, it has to get into a certain geometry, and then that's how you know what the bond angle is.
So really, we don't need to think about if it's tetrahedral.
Well, you should know it, right? It is tetrahedral.
Yeah.
So this, if it has no pi bonds, it's tetrahedral 109.5.
Yeah.
If it has one pi bond, it's trigonal planar and it's 120.
Yeah.
If it's 2 pi bonds, it's sp hybridized, it's linear, and it's 180. So let's take a look at maybe one from our workshop. I think it was number 5, and it asks you to circle or identify the electron-deficient portions of this molecule. So one thing you could do to think about this, if I took a step back, is where did this come from? All right, so how do we make this molecule? Maybe that'll make it easier for people to understand. There is a lone pair here. So let's say we start out with methanol, and it's going to react with H+. Kind of leads us into our acid-base discussion. So how do these things react? So every reaction takes place. Somebody has electrons, somebody wants electrons. Who do you think here wants electrons?
Hydrogen.
Well, take a step back. Who has a plus charge right here in this reaction? If I'm reacting these two, who has a plus charge?
Hydrogen.
So who wants electrons? Hydrogen, right? Hydrogen's electron deficient. It has a plus charge. Right? I'm not saying oxygen wants to share its electrons, but will it?
Yeah.
I mean, this is pretty reactive, right? This is acid. You guys learned about acid, right? It's reactive stuff. So these two electrons are going to attack that hydrogen. See how I lassoed them together and they're attacking there. Those same two electrons ended up where? How many electrons did this hydrogen start with? If hydrogen has a plus, if hydrogen has a plus charge, how many electrons does it have? 0.
Yeah.
Right. Good. Okay. So here's the new bond. These are the 2 electrons in that bond. Where do they both come from? Oxygen, right?
Oh, because it had to give up some electrons.
Right.
It becomes positive.
So that's why, formal charge is something we do to keep track of electrons. Now, right, so this is the reaction going forward. Awesome. Does that change the fact, if I just showed you an oxygen-hydrogen bond, who owns the electrons in that bond? Oxygen or hydrogen? Oxygen does, always. That's a fact. That's a periodic table fact. Electronegativity, fact. Physical property, right? Are physical properties man-made? Person-made? No. That's data. Physical properties are a thing. That's a real thing. Physical, right? Periodic table has periodicity. It's a beautiful thing. Me putting a plus charge on oxygen, do oxygens have plus charges floating around on them? No, this is all made up. But it's a way to keep track of electrons, which is super important because, right, electrons is the superstars of organic chemistry. So just because this has a plus charge is just a way for us to keep track of what's going on. Does that change the fact that oxygen is more electronegative than hydrogen?
No.
No. So where is it electron deficient at in this molecule?
And the hydrogens.
On the hydrogens.
So the oxygen's just being nice.
So the oxygen is just being nice. I put little delta pluses. Right? The oxygen is just being nice.
Okay.
But really, that's you know, in reality, right, this is where it's delta plus. That's where it's electron deficient. So this is a tough one, right? So people get confused with hydrogen. Carbon and hydrogen do not form polar bonds. All right, so this molecule right here is, all this is made up of is 1, 2, 3, 4, 5 carbons, and 3, 5, 7, 9, 12 hydrogens. Do I draw the hydrogens in? Absolutely not, because I'm lazy. Are there any polar bonds in this molecule? No, this is like oil, right? This is like oil, right? Maybe you've seen fatty acids. Yep, there's 5 carbons here, right? 1, 2, 3, 4, 5. I just drew one up. It's not exactly like that. Right? You've seen fatty acids that look like this, right? Some sort of OH, or carboxylic acid, and then you have a big tail. Right? I just drew it different. Right? You guys have seen fatty acids, right? This is that lipid bilayer. This is a polar end, polar covalent bonds. And this is a non-polar end because none of these bonds are polar. Because this is just carbons and hydrogens. Hydrophobic, that's right. So this is the same idea. So CH, CC, those are not polar bonds. Another example they show in here, one of my favorites, carbon dioxide, CO2. Is CO2 a polar molecule overall?
Yeah.
Overall? No. Right? It pulls equally like this.
Yeah.
Does it have polar bonds though? Yes. Right? It has polar bonds towards the oxygen, right? So just because a molecule's overall is nonpolar doesn't mean it doesn't have polar bonds. Right? But yeah. And that matters more. The polar bonds is more important, right? Because we're doing
Does that mean like
bonds.
O2 cancel?
Well, yeah, think about, so like O2, who's more electronegative, O or O? Right. So that's going to be, right?
It has polar bonds, but it's not.
Does it have polar bonds?
No, because it's the same.
Because
It's kind
there's
of like a
nothing
carbon
to
to
pull.
carbon almost, right?
Yep.
Oh, okay.
Does it have polar bonds?
No.
No. Right, is the molecule itself polar? No. There's not one end that's more delta plus or delta minus than the other. So let's say, so what if carbon CH3, CH3, right, is bonding to, pick an element. No, not that, do that. Cl. Is that going to be is that a polar molecule?
Yes.
Yes. Does it have polar bonds?
Yeah.
Yes. Are all of its bonds polar? No. Right? So I wouldn't say, right, the question is, does it have? Not are all.
Yeah.
Right? Does this have polar bonds? Yes. This one right here. Are these bonds polar? No.
So my question is, in a molecule like that,
Yep.
determining overall polarity, am I more worried about just carbon versus chlorine?
Yes. That's all that matters.
Yeah.
Right? That's only where the polarity is coming from. This stuff, these aren't polar bonds. Right? Polar bonds contribute to overall polarity. If you don't have polar bonds, I don't think you can have a polar molecule.